Okay, so we have looked at a couple of commands that we can execute to look at our network settings and change network settings, route and net shell. There's a lot of things we can do with those commands, and we haven't looked at every single thing that you can do because there's just too many. Next up, we'll take a look at ping, which I'm guessing that you have already used. Remember, ping, the main reason to use it is to check connectivity between your computer and another computer. And what we do is we send ICMP echo request packets and wait for the responses. So remember that when you use ping, you send a packet out to that destination, and if you don't get one, it's not because that computer is not available or not running. It could be because there's just no network connection, or that there's a firewall that blocks your ping request from actually being sent, and so you don't know if you get a message saying that you cannot connect to that destination. There's many things that could be wrong. However, if you do see a positive response, that is, you get an ICMP echo reply packet, then you can get information statistics on how quick that connection is, and what the time to live and so on, those things are. Okay, so once again, ping, send a message, get a reply back hopefully, and if you get a reply back, then you know that it is up and you can get some speed statistics. If you don't get a reply back, you don't know exactly what went wrong. You don't know if that machine is not working, not on the network, or if there's a firewall blocking your messages. And actually, if you don't get a response, often it's because of firewall settings that prevent these echo requests from getting to the destination. Okay, so let's say you do get a echo reply packet back from that destination, and so you'll see some output like this: reply from whatever the destination is, and then you see the number of bytes sent. In this case, it's a very small packet, 32 bytes, and it took less than a millisecond round trip, and the time to live in this case was 128. It means you could have waited quite a bit more and to check and see if that destination responds or not. Okay, to see the options available for ping, for the ping command, just type in ping space slash, that's a forward slash question mark. As with most commands, you can do that to find more options. Usually that's all we need is ping and then the destination. You may have seen the ARP command as well. ARP stands for Address Resolution Protocol, and this command allows us to display our current status of our local ARP cache, or actually even make changes to the ARP cache, which you typically don't do. We typically don't use any of these commands to make any changes. We just want to look at we just want to query the status usually. So remember, the ARP converts an IP address to a MAC address, and so this ARP cache will contain pairs of IP addresses and MAC addresses. So it's a way to check. You can search that table for an search using an IP address for a desired MAC address. You can actually add entries to an ARP cache. You typically don't do that, but you can. And you can do things like use the minus a option, so ARP space minus a or minus g. Both of these will display the current ARP entries in your cache. You can delete ARP entries if for whatever reason you believe that you should not have that MAC address. Then you can delete ARP entries, or you can add an ARP entry if you wish. Most of the time we don't do this, we just check what the cache tells us. Traceroute is another command that's good to know. Remember, we cannot use it on the Ethernet connections on campus, because traceroute is one of those things that is blocked from working, and this is also true of ping. You cannot ping machines off campus using the campus network for a lot of things, especially not the Ethernet network, because it's just considered a nuisance and not things that most people on the network usually do. So most people don't use the ping command. It's only when you're studying things like networking that you have to use ping or traceroute, things like that. On Linux machines or Mac OS machines, you have all of these commands pretty much, except it's be a little different. And I believe on Mac OS machines you would have to spell it out: TRACEROUTE, all one word. All lowercase will give you the same thing that traceRT, or all one word, does on Windows machines, and it's called traceroute. So this will display the route packets take between your computer and a particular destination. And what it does is actually does the same kind of thing that ping does, but with TTL values, time to live values, starting at 1 and then increasing until you reach the destination. Okay, this is very useful for troubleshooting the routing topology of a complex network, finding bottlenecks, finding out where things are being delayed. And the thing is, it displays the time it took to receive a reply from each router along that path to the final destination. And so you can see if one particular router has a huge delay, then you know that that's where the bottleneck is for your path to your destination. So here's an example of traceroute. In this case, I was at home and I used traceroute to display packets going to a machine in London, just to see how fast this would be. And you can see the first time to live packet just goes to my DSL modem. So it's my home modem, and it has the same address as the default gateway for my network. And you can see it, the packet that I send out and for which I get a reply, it takes anywhere from half a millisecond to about a little bit more than a millisecond. So half to 1 roughly millisecond. The next step it has to go, the next router that it'll see is my ISP provider, internet service provider's router, and here's the IP address for that. And it's still, I use CenturyLink, but it's still called, the network's still called Quest.net, because that's what the old name used to be. And so this is just a CenturyLink router in, I guess, St. Paul, and it took 21 milliseconds to get to St. Paul, anywhere from 21 to 23. And then after that it goes to another internet router. So this will typically be a very special router that runs very special protocols to provide connections to all the subscribers to the internet. And this took only another 23 milliseconds. Chances are these are in the same building, and so it's probably limited by the speed of the routers themselves, how much traffic they're seeing, things like that. Okay, for some reason they go from St. Paul to, it looks like, Minneapolis, and that took another roughly 25 milliseconds. So 25, 25, 25, we're up to 75 milliseconds. And then amazingly, I was amazed to see this, that from Minneapolis you go direct pretty much to London, or they're hiding some of the things that happens between Minneapolis and London, but it looks like you go from one city in this country all the way to London, and you actually have the IP address here for that machine, and you can see there's a much larger delay, but it's not that big. It's roughly less than 150 milliseconds to go from Minneapolis to London. It's pretty good. So the bottom line is to go from um, um, a computer at home all the way to London. You need roughly one. Well, let's not count the modem. So, okay, let's just count that too. So you need the modem router, and then you have a couple in your internet service provider. That's in this case, there's three of them. And then finally, you just need like one more hop to get all the way across the Atlantic to London. It's pretty good. And then a couple more to get to that one particular machine I was looking for. And altogether, the overall delay is, if you add up all of these, might be a quarter of a second or a little bit more than that. Let's just say a second. Even if it is a second, that's not bad. All the way, getting all the way across the Atlantic. Okay. And the other thing is, roughly speaking, you have 7 routers between you and a computer in London that I just sort of picked arbitrarily. Okay. So that's looking at the routing from a path from your computer to some destination computer, in this case in another country, across the Atlantic, across the ocean, and all that. You can also do things like do a domain name system lookup using the command nslookup. That's the name of the command, and you can say nslookup and then the type and then follow that with an argument that is any fully qualified domain name, that is symbolic name for a machine. For example, uwstout.edu. You can say nslookup space uwstout.edu and it'll tell you what the IP address corresponding to uwstout.edu is. This is used to test and troubleshoot DNS, basically check and see if your local DNS client is working, if you are actually if you do actually have access to the domain name system servers. It can be used in command mode or interactive mode. In command mode, which is usually how you use it, you just say nslookup and the host name, like uwstout.edu, to see what the host's IP address is. Remember, whenever you type in something in your address bar, what the browser has to do is ask the DNS client on your computer to figure out what that host address is. A long time ago, you used to be able to type in IP addresses in your address bar, but most systems no longer accept that. Things have changed in the recent past. So you have to find the IP address, and so the browser internally uses that IP address to get web pages at that address. Okay. You can type in a question mark to find out the list of options, as with many of these commands. So the next thing that we want to look at is network address translation, and this is important because just about every network that we use that uses IPv4 uses network address translation. You don't have to use NAT, but you end up using it because most situations will involve the use of private IP addresses on your network. And so NAT is what helps you convert any private IP addresses that you use internally to an external public IP address. So this NAT, it's usually, almost always, it's used with routing, and it's especially used for routing to the internet. Remember, private IP addresses are not routed by routers facing the internet. So if you're out on the internet, you should not see private IP addresses. It's just routers are, by default, they do not do anything with those kinds of those private Class A, Class B, or Class C IP addresses. You have a NAT to convert any IP addresses. So for example, if you're sending out a packet of information, packet of data to a website and on the internet, your NAT will translate that private IP address that you have internally into a public IP address that your whole, let's say, corporation or university or organization is given. So your organization has to have a public internet address. So everybody inside your local private network will end up using the same or similar public IP address or addresses. And so you have to picture the situation where you have an internal network. It's all private IP addresses, and there's traffic. Let's say many people using the browser, many people using browsers on their machines to talk to various servers, and they all come back essentially to just one or a small number of public IP addresses, but then use port numbers to distinguish between the individual people sending out these packets. So otherwise you would have all these servers on the internet responding to your organization's public IP address, and you won't know where to send it to. The only way we know who inside the organization used a particular server is using port numbers. So when the data is returned to the workstation, when you get data from servers outside your organization, outside your local area network, that public IP address is translated back to the original private IP address using what's called a NAT table. So you need that NAT table to do that conversion of private to public, and then when you get a message back from a server, public to private. Most of the time you see these network address translation protocol running in things like routers. You can actually do this on your own machine, and actually we sort of will do this later on in this course when we look at virtual machines. Okay, so the NAT software stores a NAT table which will be changing all the time, and that keeps track of how to translate from private to public, and then the other way around, from public to private. So here's a good example. You have a small internal network with the 10 point something 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 addresses for the internal networks. Remember, this is a class A private IP address. In this case 10.0.0.1 and 10.0.0.2, and they're connected to a switch connected to a router which runs NAT and converts the 10.0.0.1 to, in this case, the public IP address 198.60.123.101. In this case, we are, for whatever reason, we are allowed to have multiple public IP addresses. That's not always the case. We usually have just one. And so if you use multiple public IP addresses, there's no ambiguity. You know that 10.0.0.1 is this IP address ending in 101. 10.0.0.2 is another IP address ending in 102. You can have that. But most of the time, what we use to track which computer on the inside you are talking to, you use port address translation. So this allows several hundred workstations internally to access the internet with a single public IP address. So each contains source and destination IP addresses along with source and destination port numbers. And so the port numbers is what tells you which particular machine on the inside an external server is talking to. So a single public IP address is used for all workstations, but different port numbers tell you which particular machine on the outside machines are talking to. So here's another example. In this case, you have 10.0.0.1, 10.0.0.2 going to a NAT router with port address translation, and it uses single IP 198.60.123.100, but the 10.0.0.1 machine is given the port 5311 on the outside, and then 10.0.0.2 IP address machine is given the port number 3105. Chances are you will be using internal port numbers for each one of these machines too. But for this example, the main thing to keep in mind is that you can use port numbers, and they can be different from what you're using internally, and that's how you distinguish between two different computers. Okay, so to summarize these commands and IP settings, remember from last time that CIDR largely replaces the IP address class system. So we use classless internet domain routing. We can use subnetting to divide a large network into smaller networks. We'll keep looking at more examples of how you do subnetting. You can also use commands to work with IP address configurations on your local machine using netshell, ipconfig, ping, ARP, route, traceroute, nslookup, and there's a bunch more, but I think this is plenty for now. We use network address translation and enable that to allow us to use private IP address internally, which is not routed on the internet, and you have a public IP address on the other side.